Okay, let's just dive right into this explainer. You know, when most of us hear magnetic levitation, our minds instantly jump straight to the magnets, right? I mean, it's in the name. But today, we're actually going to completely flip that script. We're still exploring the fascinating, totally frictionless world of magnetic levitation, but we're looking at it through an entirely different lens. We are going to focus on the real, unsung heroes that literally make the whole thing possible. The sensors.
It really all kicks off with this one kind of provocative question. How exactly do you make solid, heavy metal just floats in midair? We're talking about replacing big, clunky physical machinery with something that honestly looks like a magic trick. But as you'll see from the data we're looking at today, it's absolutely not magic. Not at all. It's actually a highly orchestrated, super intense system of relentless observation and instant reaction. Now, to really grasp why sensors are so crucial to pulling off this illusion, we actually have to rewind all the way back to 1842. A British mathematician named Samuel Earnshaw found a pretty major physics flaw. It's called Earnshaw's theorem, and it basically says there is no stable, static position to naturally levitate a permanent magnet. Let me just repeat that because it's a game changer. Statically levitating a magnet is mathematically impossible. No way around it. If you want a ferromagnetic object to float, at least one degree of freedom has to be actively controlled. Basically, it inherently needs constant help to stay up there.
So this leaves engineers facing a pretty stark choice. Over on one side, you've got your traditional mechanical bearings. These are the clunky, everyday workhorses of the industrial world. They've got high friction, they need constant oil lubrication, and they're always going to break down eventually from mechanical wear and tear. But on the other side, magnetic bearings. We're talking zero friction, totally contactless operation, incredibly pristine setups. The catch, though, thanks to our guy Earnshaw, is that they are inherently unstable without continuous, and I mean continuous, active intervention.
This brings us to the most crucial point, and it's kind of mind-blowing. The object isn't just peacefully floating there. It's actually constantly falling. Every single second, it's in this wild state of micro-chaos where the rotor is perpetually slipping out of balance and then getting actively shoved right back into place, literally fractions of a millimeter at a time. And the absolute only way the system knows how to push it back is by watching it incredibly, incredibly closely.
And that is exactly where our unsung heroes come in to handle that relentless observation. We've got eddy current sensors. These guys are constantly measuring the air gap, any slight tilt, and the translation of the rotor. Then you have Hall effect ICs acting as rotary encoders, keeping a super precise eye on speed and angle. Plus, force measurement sensors tracking the exact forces hitting the rotor across the X, Y, and Z axes. If you take away these components feeding that live data, the magnetic field is completely blind and the rotor just crashes. It's that simple.
To really picture this in action, let's check out a 5-degree of freedom prototype machine. If you look at those specific measurement planes, the ones labeled C and D, you'll see exactly where the eddy current sensors are strategically placed right around the rotor. They're multitasking, basically. They have to monitor both the radial position, so that side-to-side movement, and the axial displacement, which is the up and down movement, perfectly simultaneously. But how on earth does the system actually use all this data fast enough to stop a crash? Well, it's this incredibly fast microsecond life cycle that we can call the closed-loop dance. Here's how it goes. Step 1, the sensors detect a microscopic little displacement in the rotor. Step 2, a digital PID controller jumps in and calculates the error between where the rotor is right now and where it actually needs to be. Step 3, the control current being fed to the electromagnets gets instantly adjusted. And Step 4, that new magnetic force recenters the rotor. Boom. And then it immediately repeats the whole thing over again.
But honestly, what is truly staggering here is the sheer raw speed of this control loop. To maintain this magical illusion of perfect stability and literally fight gravity in real time, the experimental setup we're looking at has a sampling time interval of 0.1 milliseconds. To put that into perspective, that means the sensors are pulling data, calculating the air, and adjusting the magnetic field 10,000 times a second, every single second. It's just unbelievable. Now, if you're suddenly picturing an absolute nightmare of complex kinematics equations right about now, well, you wouldn't be wrong. But don't worry, there is no math quiz today, I promise. The digital signal processors step in and handle all that heavy lifting for us effortlessly. Still, it really just highlights the immense, almost incomprehensible mathematical calculation power required to translate all that raw sensor data into physical, real-world stability on the fly. And you know what makes the math and the sensors' jobs even harder? The fact that this is a MIMO system. That stands for multi-input, multi-output. See, because magnetic fields overlap with each other, we get something called cross-coupling. Imagine it like a giant spider web. Moving the rotor in just one direction mathematically impacts all the other magnetic units. A single little shift affects the whole shebang. This means our sensors can't just act independently in their own little bubbles. Their continuous, perfectly synchronized observation is absolutely critical to keep this whole highly strung system from just completely collapsing into itself.
So you might be wondering, why go through all this trouble? Why build these wildly complex sensor networks? Well, because getting rid of friction doesn't just look cool on a lab bench, it fundamentally changes the world around us. These hyper-fast sensor networks power some absolutely incredible, diverse stuff. We're talking about utterly pristine semiconductor manufacturing clean rooms, where even a speck of microscopic mechanical dust would totally ruin a microchip. We're seeing 6 degree of freedom magbots that can autonomously drop off and pick up payloads for agile factory manufacturing. We're even seeing this tech scaled all the way down for total artificial hearts, and then scaled way up for massive 50,000 RPM air compressors.
Let's actually look at that heavy industrial scaling first. Just by swapping out your standard, conventional compressors for MagLev centrifugal compressors, the changes to a facility are honestly night and day. You go from dealing with noticeable, grinding noise and frequent, super messy mechanical maintenance, straight to near-silent operation and barely any upkeep. And because this sensor-driven MagLev completely eliminates physical friction, these massive impellers can safely hit over 50,000 RPMs without a single drop of oil. That nets the factory up to a whopping 30% in energy savings.
And just to show you how incredibly adaptable this technology really is, let's contrast that massive industrial air compressor with literally the most delicate application imaginable. Researchers right now are utilizing double-stator bearingless motors to design a MagLev pump for a total artificial heart. By using these exact same ultra-precise displacement sensors to keep a tiny rotor perfectly suspended right inside a patient's chest, they can prevent the mechanical wear and tear that traditional pumps inflict on extremely fragile human blood cells. I mean, they are scaling down magnetic levitation to literally pump life itself. How wild is that?
So what you should really take away from this explainer today is that the magic, well, it isn't actually in the magnet at all. The future of friction-free motion doesn't rely on building better magnets, it relies on faster, smarter sensors, and eventually AI. It's the silent, relentless 10,000 times a second vigilance of these unsung heroes that actually makes the impossible a reality. So I'll leave you with this. If a network of sensors can suspend solid metal in midair and safely pump a human heart without touching a single drop of blood, what impossible physical barrier will they break next? Think about it. Thanks for joining me, and we'll see you next time.